that. 1 times 2/5, comma, f of that. 2 times 2/5, comma, f of that. 3 times 2/5, comma, f of that. And 4 times 2/5, comma, f of that. All right, and now if we write out the sum, can we just go straight to sigma notation maybe?
Yeah.
It's
I haven't
not
copied this down.
It's not the, isn't it like f of, like, the previous one though?
Yeah, that's what makes this kind of annoying. So this is actually going to be harder. Well, okay, maybe I will just kind of write it out. Except I sort of don't feel like it, but I'll just do it anyway. The sum therefore is going to be the area of the first rectangle, but the area of the first rectangle now is 2/5 times the height of that rectangle, which is f of 0 times 2/5. And the next one, the next rectangle is going to be width of 2/5 times the height of 1 times 2/5. And I'm just going to write ... 2/5 f of 4 times 2/5. So Robert Rose is right. We're now kind of like off by 1 in a sort of annoying fashion. All right. So, all right, because of you guys are sort of experienced computer science programmers, you probably have a suggestion now, which is to write the sigmas starting at 0.
Yeah, that's what
Unfortunately, I don't want to do that because it is too hard. It gets really hard because, for the following reason, these formulas all work very nicely when you all always start the index at 1. And for that reason, upon even though it's more annoying, I would like to institute a class rule that we're not mess with the indices, because that's a very advanced and difficult thing to do. So unfortunately, if I'm committed to starting with I equals 1 and going to 5, it gives me a slightly more annoying formula. What is the formula now?
2/5 I minus 1 times 2/5.
Yeah. When you see that? And to do this, you just double check this, right? You plug in when I equals 1, yeah, it works. Plug in when I equals 2, yep, it's matching up. Plug in the last term will be when I equals 5, so everything's right. Unfortunately, is everybody okay with this? Yes.
Distribute or when you multiply. It's going to be all right.
Yes, I don't know what you just said, but what I'm going to do, I'm just going to continue this process. We might just quit this if it starts to get really annoying. So what do we get here? We get now so I now have to plug 2/5 I minus 1 into f. It's really not that bad. Let's just do it. So we get, this is going to be negative 2/5 I minus 1 squared, right? Yo.
You just add 5 at the 4.
Just give, what do you mean add 5 before?
You would add 5 and have 1 and 4.
Yeah.
What?
Because it starts at f of 0 and that's easy to calculate, so you just do that.
Just go from, yeah, there are other ways to do this. I'm trying to build a particular skill. I'm not saying this is the most efficient way to do this, but does everyone agree that this is right? Okay, so, and then you have to just do this out, right? So you get 2/5. We're trying to do some practice here. So we get 2/5, and this is I equals 1 to 5 of, well, now this is negative 4/5 times I squared minus 2I plus 1 plus 5. Then what? Yeah, you just keep going. So this is 2/5 I equals 1 to 5. Yeah, write small. Of negative 4/5 I squared plus
over 25.
Where?
Negative 4.
Oh crap.
25.
That should be 25. Yeah. Negative 4/25 I squared plus 8/25 I minus 4/25 and then plus 5. Does everyone see what I'm doing? I'm just cranking it out. I'm just distributing, I expanded out the I minus 1 squared. Now I'm distributing the negative 4 25ths through. 5 minus 4 25ths, whatever that is, what is that? That's like something,
121 over.
just 21 25ths.
120, 121.
And now, finally, I can expand this all out, and,
It's one.
did I mess up yet?
Yeah, it should be 121 over 25.
125 minus 121.
Oh, yeah, crap, 121. So now, when I expand this all out, I get, everyone do this with me. What do you get?
I got
Wait, you want it to actually like do
Yeah, just like, call it out. I don't know. Get negative 8 over 125. Sum from I equals 1 to 5 I squared.
Plus 16
Plus
over
16 over 125. Sum I equals 1 to 5 of I plus 242 over 125, sum I equals 1 to 5 of 1.
Oh my.
I think I did that right?
You're
It is. Little fire.
Yep, looks good to me.
My signals are fresh.
Now compute these using the formulas. What's the other relevant formula? What's the sum from I equals 1 to n of just I? This is n plus 1 over 2.
I'm so ready for this.
So finish this computation and tell me what you get. Yeah. All right,
That's what
I
I
got 202 over 25. Is that what you got?
Yeah.
All right, so this is in fact 8.04. All right, and based on the geometry of this, I can guarantee you that the exact area under this curve is somewhere in between 6.48 and 8.04. All right, so let's talk about this for a minute. These things that we just did, they have names. The name for what we did over here, I just said lower estimate, but actually this goes by a more general name. This is called, the name for this is, we call it RRAM, which stands for, this is a right rectangular approximation method. And in a right rectangular
Is that a registered
approximation.
acronym?
What's up?
Is that a registered?
That is a registered acronym.
Oh.
The right rectangular approximation method is exactly what it says. It's a method. Specifically, it's an approximation method, so it's a method for approximating the true area under the curve. It's a rectangular approximation method because it uses rectangles, and is a right rectangular approximation method because it uses the value of the function at the right-hand endpoint of the subinterval. I will say that again. It is a right rectangular approximation method because you take the interval, you divide it up into a bunch of subintervals, and then for each subinterval, you have to choose how high to make the rectangle. And the answer is the height of the rectangle is determined by the value of the function at the right-hand endpoint of the subinterval. Make sense?
LRM.
Okay, so what do you think we call this method?
LRM.
This is LRAM. And LRAM stands for left rectangular approximation method. And in the left rectangular approximation method, you take the interval, you split it up into subintervals, and for each subinterval, you draw a rectangle. And in this case, for any particular subinterval, the height of the rectangle is determined by the value of the function at the left endpoint of the subinterval. Sound good? Okay, so what we have, and now we can ask some deep questions. Like, does the right rectangular approximation method always give you an underestimate? And vice versa?
No.
Yeah, Winnie's shaking her head. When does it?
When it's concave up.
What is decreasing?
Well, no, I was thinking.
Or like,
that's
or
what I meant.
I would think that.
When
If it's
at
Wait, what are you
yeah.
asking? What is it what?
Let me be more specific with my question. I'm asking, when is RRAM an underestimate and when is it an overestimate? When is LRAM an underestimate and when is it an overestimate?
Oh,
Arnold said
LRM
something
is
smart.
underestimate.
Arnold did say something smart. I heard a bunch of people mumbling about concavity. That sounds right at first, but in fact it's not. Arnold.
Oh, concavity don't matter.
Concavity does not matter. What does matter?
If it's going up or down, or like
Yeah.
increasing or increasing.
If it is going up or down, let's draw some pictures. If I have a function which is decreasing, and I want to find the area under that curve, like my curve here, and I split it up into a bunch of subintervals, then suppose I do LRAM. Well, if I do LRAM, what I am essentially doing is for every subinterval, I am picking, so this function is decreasing and I'm using LRAM. What I am doing with this function is I'm picking one of the points on this function to be the approximation of that function on that subinterval. But by using the left endpoint, since this function is decreasing, at every single moment the y value is going down. Since the y value is going down, over any particular subinterval, the y value will also be going down. And since the y value is always going down, the tallest the function will ever be on that subinterval is at the left-hand endpoint. Thus, LRAM has to be an overestimate. On the other hand, suppose I draw an example of an increasing function. If the function is increasing, and I use LRAM, then if we draw a similar kind of picture, well now, by using the left endpoint, I am going to produce an underestimate. Because since the function is increasing, at every single moment the function is getting bigger. By letting the left endpoint of the subinterval be the approximation, then it's going to produce an underestimate because that is the lowest the function is on that subinterval. Is everybody with me? Should I draw the other two pictures? No, not necessary. Okay, good. Okay, so now we get to something kind of deep and fun. How can I make this method better?
Make a formula.
Winnie.
Make the subsection smaller.
Yes, what you can do, if you want this to be better, I have guaranteed that the answer is somewhere between 6.48 and 8.04. If that's good enough for you, great. If you want it to be better, then what you need is more rectangles. The more rectangles you have, the better your method is going to be. And you get more rectangles, just like Winnie said, by making more subintervals. And in other words, what we're going to do is we're going to let the width of the subintervals be smaller and smaller. And how might we get the answer to be perfect?
Limits.
Yeah, go all the way. Let the number of subintervals go to infinity. All right. So turn to the next page in your packet. Is the function y equals x squared from x equals 1 to x equals 4. I think we're gonna. Well, okay. So here's the function. The function is what is it again? It's f of x equals x squared plus 1, and we want to know the area under the curve on the interval 1, 4. Okay. Well, there are two ways we can do this. So here, I'll draw this now. Or I'll try to draw this. It's going to look better on your paper. When you plug in 1, you get 2, right? And that's 4, 6, 8, 10, 16, 18. And when I plug in, I'll just get the rest of the points. When I plug in, well no, I'll just get the last point. When I plug in, so that's 2, that's 4. When I plug in 4, I get 17, right? Okay. So we have something that looks kind of like this. I think it's 17, right? If I plug 4 into the function? Yeah. Okay, I get something function that looks like this. And what I want is the exact area under this curve. This is what I want to know. All right. Well, we have two options. We can do a lower estimate or an upper estimate. On page 2, they ask for a lower estimate. If I want a lower estimate, what should I do? LRAM or RRAM?
You do
LRAM.
LRAM, right? But guess what? I hate LRAM. That's what I learned on the front board. LRAM is annoying because of this I-1. So let's skip page 2 and let's just go straight to page 4. That's all we have time for. It's the first time I made emails and happy all year. So on page 4, we ask for an upper estimate. All right, so we have 10 minutes. Oh man. So let's do this. Let's come up with an upper estimate. Well, if I want an upper estimate, then what do I have to use? I'm going to use RRAM. Okay, so now, how many rectangles should I use? Well, I'm going to use n rectangles. N rectangles. All right, well, if I'm going to use n rectangles, what should be the width of each rectangle?
0 plus.
No.
is not
Width of each. No, everybody, please focus. What is the width? It's not a hard question. What should the width of each rectangle be?
Divided by
0 over n.
No, please focus. Using n rectangles.
No, 3 over n.
What is the width of this interval?
3 over 8.
3. So this was an easy question. The width of each rectangle should be 3 over n.
Sorry.
So let's just call that delta x. That's going to be the width of each rectangle. Okay, let's draw the first rectangle. Well, the first rectangle is going to look something like this. Oh man, looks much better on your paper. Oh well, too late. So what is this? What is this point? What is this point down here?
1 plus delta x.
1, let's just call that 1 plus delta x. That seems like a good idea. And then what are the coordinates of this point up here?
1 plus delta x, comma, f of 1 plus delta x.
Yeah, let's call it 1 plus, okay, so yeah, so it's 1 plus 3 over n, comma, f of 1 plus 3 over n. You can make that much bigger. Okay, how about the second rectangle? What are the dimensions of the second rectangle going to be? What's that point now down here?
One.
What?
Plus 2.
Nope.
1 plus 2.
1 plus 2 times delta x. Right, because look, this is 1, right? We move, if the width of each rectangle, if the width of each rectangle is 3 over n, then that will be 1 plus, that's going to be 1 plus 2 times delta x, etc., etc. And the next one will be 1 plus 3 times delta x, right? Say right. Okay, good. So I could even call this first one 1 plus 1 times delta x. Because to get to this point, I go to 1, and then I go 3 over n more. Richard, with me now? Sure. Okay, good. So how about this next point? What are the coordinates of this next point?
1 plus 2 delta x.
That's 1 plus
2 delta x.
2 times 3 over n, comma, f of 1 plus 2 times 3 over n. And then this next point will be, I think this is pretty hard, right? This next point will be 1 plus
3 times.
3 over n, comma.
no, 1 plus 3 times 3 over n, comma, f of that.
We're dividing it
Right? Again, the width of the total interval is 3, and then I'm just going to write kind of like dot, dot, dot. The width of the total interval is 3. If I want n rectangles, then the width of each rectangle will be 3 over n, and I get to each one of these points by going 1, and then I skip by delta x, skip by delta x again, skip by delta x again. Okay, so what is the total sum under this curve going to be? Well, it's going to be, what's the area of the first rectangle?
1 plus 3 over n times f of 1.
No, careful. What's the width of the first rectangle? 3 over n. And what's the height of the first rectangle?
The f of 1 plus
3 over 1.
Okay, and then what's the area of the second rectangle? Width times height, right?
Yeah.
So that's going to be, what's the height of the second rectangle?
1 plus
2 times 3.
1 plus 2 times 3 over n. Okay, etc., etc. What's the height of the last rectangle going to be?
3 over n times.
F n times 3 over n.
Yeah, now I've moved over n times, right?
Yeah.
And in fact, that's right, because that should be f of 4. Okay, can we write this out in sigma notation?
Yes.
What is it?
S equals 3 over n, the sigma notation thing. I equals 1 and n on the top, and then the sum of f, 1 plus 3n, 3i.
Yeah, I'll just write it as I times 3 over n. Okay, if you got this far, that is really good. This is the hard part, in my opinion, is drawing the picture, drawing the rectangles, thinking it out, counting one at a time, kind of picturing what's going on, the width of each rectangle is 3 over n, how much we have to move over. All right, now we just have to crank it out. Unfortunately, we're going to go really fast because we're running out of time. So this is 3 over n times the sum from I equals 1 to n. Now we just have to plug that into this function, right? So the variable here is like I. So this is like 3 over ni plus 1 squared plus 1. Are you with me? Say yes. Okay, good. Now, going very fast. We get 3 over n times the sum of n. That's going to be 9 over n squared. I squared plus 6 over ni plus 1 plus 1. All I did was just multiply out that square. And now, let's split this up into 3 separate sigmas. What are they? Well, I'm going to get 27 over n cubed sum I equals 1 to n I squared plus 18 over n squared sum I equals 1 to n of I plus 6 over n sum I equals 1 to n of 1. Do you agree? I think I did that right? That was just algebra. Okay, now I'm going to apply these formulas. This is 27 over n cubed. What's the sum from I equals 1 to n of I squared? It's n plus 1, 2n plus 1 over 6. And this is 18 over n squared, n plus 1 over 2. And this is 6 over n times, what's the sum from I equals 1 to n of 1? Just 1 plus 1 plus 1 plus 1, n times, so it's n.
I have a question.
Yeah, did I mess up somewhere?
There are 2 1s. So like, why?
Yeah, so
how
that
did
made
you
it
get
2.
rid of it?
So that's why it was 6. Sorry, I just did that. Cool? Okay, so I get this gigantic formula. What does this formula actually represent? I need someone to tell me in words, what does this formula actually mean? Ian.
If you're gonna split it into n rectangles, this is the area that you'll get using this method.
Yes. This is whatever this disgusting formula, you can think of this as a function. It's a function which returns the area under the curve if you use n rectangles. So this is not the exact area under the curve, it's the area under the curve as approximated by n rectangles. Okay, and can I fix some of these? The bell's about to ring. But I can do lots of cancellations, right? This 6 becomes a, this becomes a 2, this becomes a 9, this n cancels and I get n squared here. This, one more minute, this becomes a 9, one of these n's cancels, and these n's cancel. So what I really have is a kind of formula which looks something like 9, 2n squared plus 3n plus 1 over 2n squared. I think I did that right. Plus 9n plus 1 over n plus 6. That will give me the exact area under the curve given n rectangles. Okay, here comes the glorious moment. What do I do now?
Limits.
Yeah, the approximation gets better and better the more rectangles you use. So if the approximation gets better and better the more rectangles you use, then let's just let n be the biggest possible number we can think of. Plug in 1,000,000. If we plug in 1,000,000, what am I going to get? I'm going to get almost exactly the correct area because we tediously computed this formula as representing the area under the curve if you use n rectangles. So let's just use 1,000,000 rectangles. Why not use?
Infinity.
Infinity. And so if we take, this is the solution to the area problem, which we again accomplished in just one class. If you want to find the exact area under the curve, find the area under the curve using n rectangles, and then let n be as large as possible. If we let n go to infinity, what do we get? What's this?
A lot.
What's this first one?
9.
That's 9, and this is
9.
9, 6. The exact area under this curve, believe it or not, is precisely 24. All right. You guys feel like you get this? Sorry, that was a little bit rushed. Have fun at Wallops. We will have class again. We will have class again. I don't even know when. When do we have class again? Monday? No. Yeah. Monday after Wallops. Bye, period 8.